D'accord. Et non, comment faire? OK. Mmh.
Hello. Hello, if you can all hear me.
Yeah. Yes.
Thank you. Yes, thank you. So hi, welcome to this very first session of Formats. My name is Xianming Ho. I am delighted to chair this session. So today we will have two very interesting papers. The first one will be on the explainability of safety violations in real-time systems. The second one is about pattern matching for time patterns. So if you have attended the keynote speech, you might know these topics are very interesting also in other application domains such as financial services. So I'm very interested and look forward to listen to this talk. So let me welcome the first speaker, Thomas Marie. Thank you.
Hello, can you hear me?
Yes, thank you.
Thank you. So, do we have to talk now?
Yes, if you can try to share your screen. Yes,
okay.
I can see your screen. Thank you.
So I don't really know how it works. So we see the video and there is some question after.
It's fine. Thank you.
Yep.
Sorry, I can't hear you. Sorry.
So are we supposed to watch the video or do we have to make a presentation? Because I don't hear the sound.
So I can see you're playing the video, but I couldn't hear any sound from it.
Because because I'm not playing the video. So I don't know who shared the video.
On formal verification and validation,
it's okay now.
is explaining safety violations in a real-time system. I work with Tao Dong and Gregor Gessler, and I'm Thomas Marie. So our targeted system is the embedded and real-time system, such like medical devices or transportation. In the state of the art, there is much effort on formal verification and validation, and also in practice. But when we look at the headlines, accidents still occur. The system, therefore, they need to be accountable. So it means that in case of failure, the failure can be explained. And explanation, they can be useful in different contexts. So in design phase, when an engineer runs some model checking or some test and it fails, then you get some counterexample, but it might be too long in order to be understandable. So you can use an explanation. And also at runtime, so it can help experts assign legal liability because finding the cause of a failure is really time consuming. There is some informal requirements on explanation. So it should be concise enough in order to be understood. So a concise excerpt of the observed execution. And it should also be precise. So on events, so the relevant element for entailing the violation. So in order to satisfy those informal requirements, we choose causal explanation. So they only retain the events that are causally relevant for entailing the violation and for some notion of causality that we will define in this presentation. There is some specific requirements which are challenging for embedded real-time system. So we have the dense time or the infinite state space and also the partial observability. There is only little existing work in the state of the art regarding causal reasoning and abstraction. And our objectives are to identify the non-deterministic choices for the system that cause the property violation. So an overview of what we do. So this is our input. We have a model, which is a time automata.
and it describes the behavior of the system that is unsafe. The safety property P by focusing on non-deterministic choices of the system, so the unsafe system. This sketch will be used through the presentation as a summary. So first thing, the model and property. So we have a running example, which is a fault tolerance protocol. So we have a set of events. Some of them are fault, like the F event. And the property is that the model recovers from the fault, so the faults. Some fault like F or F3 entail the violation, and some other fault can be compensated by fallback mechanism B1 or B2. But at some point there is some timeout that progress into the execution and can even lead to the violation. So the violation of the property is reaching the location L7 or L5. There is also one behavior. So if there is two discrete events E in a row, and the delay between the two events is greater than 1, then it leads to L7, which is a violation. So this is the model we want some explanation on. And now, this is our observation, so the time log. And the objective of the time log is to identify the behavior that caused the property violation. And in that behavior, there is the non-deterministic choices that cause the property violation. So a time log is a time automata. There is one clock, it is deterministic and acyclic. So it captures some timing uncertainty and also partial order events. So why do we want partial order events? Imagine that you have some multiple observations from different components. Then in this case, there might not be a total order on the event of the observation. So it can be captured by a time log. So this is the time log for the running example. So either we did 2E in a row with some delay which is strictly greater than 1, or we did the time log 2 or F3 that entailed the violation. So the observable alphabet, so the events of the time log, is only a subset of the total events. So now we can capture the behavior, the observed behavior, but we still need to explore the alternative choices in order to compute the causality. So we are going to build the log observer, and the method is called the completion. So we add one location, which is the sync location, and when a behavior of the log ends up in sync, it means that the behavior is not consistent with the log. So for that, we take the complementary transition for each transition. So if we have C greater than 1, then it's C lower than 1, and we do E and goes to sync because it's not consistent with the observation. And it's the same for all the observable events that are not observed. So T2 F3 are not observed, they go to sync, and the same for in the log. So now we have AP, so the model plus LC, the log observer, and we are going to compose them. So we can compose two time automata, and in the location we have a couple. So the first item is the location in the model, and the second one is the location in the log. So we know what behavior are violating the safety property and what behavior are consistent with the log. Now, we are going to define some abstraction on the time automata. So, we have an infinite state space, and we are going to use symbolic abstraction in order to reduce the state space to a discrete state space, so we can compute the causality. So the first B-simulation is the strong time abstracting bisimulation. So it's a bisimulation on the node, so on the time state of the time automata. So if we take two time states which are bisimilar, then it means that for any discrete event, the successors are also bisimilar by the same event. And for the time passing transition, so if we have two time states bisimilar, then for any delay, so a delay is a time passing transition and the delay is a positive real, then there exists another delay such that the successors are also bisimilar. And on top of that, we have two conditions. The first one is that the location must be the same for two bisimilar time states. And the second one is that we don't mix the accepting state, because in the model, accepting means it is a state of violation. And we don't want to have ambiguity about whether a behavior violates the safety property. So now we are going to build the time abstracting quotient graph. So we had a time automata, and the quotient graph is a label transition system. The set of state will be the set of class of the B-simulation. So it will be the set of time states that are bisimilar with each other. A state will be initial if it contains, so it is the class that contains the initial time state. And a class, so a state will be accepting if the class, it contains the time state which are accepting. For the set of events, we have one additional symbol delta. So it will be used for every time passing transition. And now we don't have any more delay in positive reals. We only use the symbol delta. And for the set of transition, so there is a transition between two classes if there is a transition between the member of the class, so the time state of the class. So it's the same for the time passing transition. We have delta if there is a delay between two members of the class. And in practice, we use the tool minim, which is an integrated tool in Chronos, to compute the quotient graph for the strong time abstracting bisimulation. So for our running example, so this is the time automaton, so the model composed with the log observer. We are going to compute the quotient graph. So now we have a label transition system. We have one additional event delta for the time passing transition. And instead of having guards, we have some time constraints, so time information in the state for every clock of the system. So now we have a discrete event system. We can compute the level of choice. So the level of choice, it is the base of the causality, and it answers the question, how close is the system to violating the required safety property? So it is a mapping between the state of the system and an integer or infinity. And the higher is the level of choice, the further we are from the violation. There is some condition, so some property about the level of choice. The first one is that if a state is accepting, so if it's state of violation, then the level of choice is 0. So it means that there is no choice to be made to violate the property because it's already violated. Because it's a safety property. The second property is that if a state in green is non-corrigible, so it means that there is no path that leads to the violation, then there is no finite number of choice for the system to be made in order to reach the violation. The next condition is the non-choice state. So if all the successors of the state have the same level of choice, so whatever choice the system do at this point, the resulting level of choice will be the same. So it will be the same as the successor. The next condition is that if a state has different level of choice in the successor, so it's 1 plus the minimum of the level of choice of the successor. So to get some intuition about 1 plus the minimum, so the worst case scenario that can happen is when we pick the minimum level of choice of the successor. We are the closest from the violation, and it is a choice of the system to pick the minimum. So it's 1 plus the minimum. And also we want the level of choice to be maximal. So now we are going to define another bisimulation. So it is the strong bisimulation. So we have a label transition system. And if we take two states, they are bisimilar if for any event the successor are also bisimilar. And we have so also we don't mix the accepting state like before. And we have a theorem that says that two strongly bisimilar states have the same level of choice. So it is a useful result because it means that if we take a class for the strong bisimulation, then the level of choice for the state in that class will be the same as the level of choice for the state in the quotient graph, so the state where the state is that class. So we can compute the quotient graph for the strong bisimulation before computing the level of choice. So this is what we are going to do. This is the quotient graph for the strong time abstracting bisimulation. We compute the another reduction with the strong bisimulation. So in practice, we use CADP for computing the quotient graph on the discrete event system. And now we can compute the level of choice. So it's displayed here in blue. So we can see that the states violating the safety property are in at 0. And the states where we recover from the fault are at infinity. From that point, we cannot reach the violation anymore. So now, the things to do is to remove all the behavior that are not consistent either with the violation and with the log. So we want only to explain the behavior that are violating the safety property and that are observed. So we can remove the other one, and we have a later graph. And now we can compute the explanation. So it will be based on the level of choice. So if we look at different trace, like this one, we want to know what is relevant and what transition is relevant regarding the level of choice. So if we take the F1 transition, the one that increases the level of choice, it leads the system farther from the violation. So it's not that relevant to put in the explanation. So if we take the next one that decreases the level of choice, so it's not that relevant either, because it is compensated by the next event, which is B1. So for us, the transitions that are relevant regarding the level of choice is the one that reduce definitively the level of choice, such as the transition B2 and T2 in red. So they reduce the level of choice, but they are not compensated in the future. Now that we have defined the effective choice transition, we can define the safe alternative. So when in a state there is an effective choice transition, then any transition that instead of decreasing the level of choice, increase the level of choice will be called a safe alternative. And there will be display in the explanation to show that there is some alternative safe scenario that avoid the violation. So now we have multiple traces to explain. And we can each time compute the effective choice transition in red. But now we have a problem. So if we look at the transition T1 there, so it decreases the level of choice. It is an effective choice transition. But if we look at the next trace, then it depends whether it's followed by B1 or followed by F3. So it is a problem. We have some ambiguity. And to resolve this ambiguity, we are going to split the graph. So for splitting the graph, we compute for each state the maximum reachable level of choice. But there is some state where it depends on the successor. So in this state, whether we take B1 and the maximum will be 2, or in this state, we take F3 and the maximum will be 1. So when it depends on the successor, we split the state like that, and it is a fixed point operation. So we start by splitting S2, then we split S0. And once we have done that, we have no more ambiguity about the maximum reachable level of choice, and no more ambiguity about whether a transition is an effective choice transition. So now we can extract the subgraph from the split graph, and by keeping only the behavior with the same size of explanation. So we keep only the path with the same size of explanation. And it is a conservative operation. So each path in the original graph, they end up in one of the subgraphs. Now we are going to define the delta sequences. So if in the subgraph we have a time passing transition in a row, so a delta sequences, then we want to say that consecutive time passing transition is only one big time passing transition. So the intuition is to get a more concise explanation and also to get a better estimation of the delay. So once we have found those maximal delta sequences, we collapse them into one delta transition. So like that. And about the estimation of delay, so just after computing the time abstracting quotient graph, we have some time information in the state. And for each clock, we have a upper bound and a lower bound. And if we compare those bounds in the origin and the destination of a time passing transition, then we can infer a conservative constraint on the delay, so the time that passed between the two states. And if we do that for every clock, we can refine this constraint, and we can get an estimation of the delay. So in the running example case, so we only add that in the origin it's x strictly lower than 1 and x strictly greater than 1. So we can only infer that the delay delta is strictly higher than 0. So now we have computed the effective choice transition after splitting and extracting the subgraph. We have collapsing the delta sequences and do the estimation of the delay. We are going to abstract away the non-effective choice transition. So the transition that we don't consider relevant, we are going to replace them by non-deterministic tau transition. And then we are going to do the determinization, and we have the explanation. So this is the explanation that we have from the running example. I added in green the safe alternative computed before in the quotient graph. We can see that the explanations are lighter than the model. And the first explanation is that we did F3 instead of a success. The second one is that we have waited too long. So on the other explanation, for the explanation of size 2, we did T1 then F3, or we did B1, then T2. So this is the relevant event that entailed the violation with respect to the level of choice. So in the paper, we did a case study. The model is a Pacemaker model. So it's taken from modeling and verification of a dual chamber implantable pacemaker. It's quite a sizable model. We have 5-time automata. It is a multi-component system. And we have an unsafe earth model, which is 2-time automata. And we have a safety property. So it states that the delay between 2 ventricular events should not exceed 1 second. And regarding that property, the earth model is unsafe. But when we compose the earth model with the pacemaker, then the pacemaker is inducing a ventricular event, and the model is safe. So we just change one parameter, we increase one parameter in order to make the system unsafe, and we want to know if the explanation is going to show us that there is a problem with that parameter. So the third point is we have a time log. So we have a contour example generated with UPAL, and from that we have computed a time log. And this is the respective size of the graph that were used in order to compute the explanation. So the first thing we can see is that when we compare the size of the explanation with the size of the model, it's really lighter. And also that just after computing the level of choice, so when on the quotient graph, when we remove the behavior that are not consistent with the violation and the log, then the graph are much more lighter. So this is the explanation that we have in the case study. So it can be read easily because there is only a few transitions. When we see the beginning of the observation and the safe alternative, they only say that the earth model, it should do a ventricular event or do some event that will imply a ventricular event. So it's not that informative because we already know that the earth model is unsafe. But at the end of the explanation, we have some timing constraint and there is some internal event of the pacemaker. So it's good because internal event, they cannot be observed. And if we look at the guard and the timing constraint we have in the explanation, then we can see that it's only enabled because we changed the parameter. So we can recover from the violation. So to conclude, so we did a formalization of a causal explanation. It retained only the relevant part of the violating execution by focusing on branching. It's based on time abstracting by simulation and display safe alternative scenario. We have a prototype tool which is implemented in Python, and it uses Chronos for manipulating time automata and computing the strong time abstracting quotient graph, and CIDP for manipulating the discrete event system and the strong by simulation quotient graph. So for future work, the first thing is to introduce controllability. So in the pacemaker case study, if we treated the earth model as an hostile environment, we could have a more precise and concise explanation. The second option is to use true concurrency model for displaying the explanation, for example, PetriNet. And the last point is to extend the tools and theory to a more expressive system like hybrid system. So thank you for your attention.
Thank you very much for this very interesting presentation. Do we have any questions for the paper and for the presentation? Yes. Eugene, please.
Yes, I can speak yet. Can you hear me?
Yes.
Very interesting approach. But have you tried your explanations on real engineers? Do they understand?
Can you hear me?
Yeah.
Yeah. So for now, it's still a prototype. So we didn't try the explanation on the real like industrial case study.
No, I mean, not even for your toy examples. Have you shown them to some real practitioners, non-academic, without PhD?
No, not yet.
Martin?
There's a question by Etienne André on, or maybe Thomas. On the question answers.
On the question, yeah, if you can click that and you can see the question.
So any hint on how to extend to hybrid automata? Can you still find a quotient construction? So for now, the limitation is that the level of choice is computed on a discrete event system. So because on hybrid automata, we have infinite state space, and it's so it's bigger than the one on time automata. So one first approach could be to use some abstraction to reduce that to a discrete event system. So we could use the same technique. Or the other approach that we are looking into now is to define the level of choice, which is continuous. So this is the two approach we consider for that. And so the level of choice, instead of being some integers, it will be continuous reals or defined on a continuous domain.
Okay, I think we have some other question.
So your notion of relevant effective choice seems to be related to a notion of entropy. In these choices reduce these choices reduce entropy. Could you comment on this, please? So we can see the important thing about the level of choice is to see. So it tells us how far the system in terms of choice left is from the violation. So when a choice is made and it decreases definitely the level of choice, then in the future there will be less choice to do to violate the safety property. So if we consider the entropy of the system as the number of choice left, then yes, it could be seen as entropy. So for future work, we could work on different notion on how far are we from the violation, such that, for example, entropy, or for example, some energy left to violate the safety property. So this is some design choice that could be really interesting for explaining why do we reach a violation at some point. Yeah.
Thank you very much. Thank you. So do we have any other questions? If no, then thanks very much again, Thomas. It's a very nice presentation, a very interesting topic. Okay, so I think we can move to the second talk of the session. It will be by Professor Eugene Sarin. It will be on the complexity of time pattern matching. Thank you very much.
Hello, let's wait for the video. Should I present it live, or if you want?
I have asked the technical chair to play the video, so we can wait
Okay.
for 1 more minute. No worries.
Okay,
Thank
okay.
you.
Hello, I'm Eugene Assarin, and I will speak about the complexity of the time pattern matching. It's a joint work with Thomas Ferrer, Dejan Ničković, and Doan Ulus. It was done by Zoom from 4 big cities, but it was started many years ago in Grenoble, in Verimag, in the group of Oded Mahler. In fact, it was in 20th century that we invented with Paul Caspier and other time regular expressions. It's in 2014 that Doan Ulus, at the time Odet's PhD student, suggested to match patterns described by a timed regular expression in a big timed word. We have presented this at Formats1, and we have developed several variants of this problem of this algorithm, also tools and application involving offline and online pattern matching using automata, derivatives, and so on and so forth. On the other hand, in parallel, a similar line of research was developed by Japanese colleagues. Recently, when writing a comprehensive journal paper on time pattern matching, we understood that one particular point was overseen, that we have forgotten to address the complexity questions. And in this work, we try to address this issue. Let me start by recalling briefly our old developments on time pattern matching. What is pattern matching in general in our context? Given a long file, a long text file W, and the regular expression, find all the occurrences of the expression in the word or in the text or in the file. Classical solutions are often based on finite automata. They are mostly polynomial in complexity. The problem is polynomial in complexity, surely. Many tools are known, such as grep, sed, regex engines of many programming languages and word processors. We extended it to timed signals as follows. For us, a signal is something like that, Boolean valued, with 2 variables p and q, and in continuous time, defined over a finite interval of time. An expression is something like that. This one says, have p and q during some time together, followed by q which becomes false, followed by q which becomes true. All that should have a duration between 4 and 5. And after that, there should be an interval where p is false. There are many subintervals which corresponds to this expression. For example, from 1,3 to 6,8. Here we have p and q, not q, q. The duration is 5, and there is some duration of not p afterwards. We say that the interval or the couple of dates 1.3, 6.8 is a match. There are some other matches, many other matches. So I repeat, we consider time Boolean signals over m Boolean variables. They are continuous time, and Boolean variables switch values from time to time. We don't care about glitches and other discontinuities. As for time regular expression, they are formed from propositional variables, which means P is true during some interval. Their negation, they include concatenation and disjunction. If one wants it, one could put conjunction as well. Iteration, we don't like Kleene star because we don't like zero duration signals. For that reason, we prefer Kleene plus, that is, iterate phi as many times as you want, 1, 2, 3, etc. We need time restriction. It is make behavior described by phi during time which is in the interval I. Sometimes we want to consider expressions with complement. Here you can see several examples of expressions. The semantics is defined in an obvious way. The only important thing that is its type. Indeed, we say that a signal W from time point t to time point t prime satisfies an expression. Please skip this definition. What is important that we associate with each expression and signal the match set, that is the set of couple of dates that t is less than t prime, and the interval between t and t prime of the signal W satisfies the expression. The problem of time pattern matching is thus, given a signal and an expression, compute the match set. The solution of 2014 was based on the well-known data structure, a zone. Those who know the model checking of timed automata, they know that zones are of any dimension are very useful. However, we will use only two-dimensional zones. A two-dimensional one is a subset of R2 described by 6 kinds of inequalities: lower and upper bound on x, on y, and on x minus y. It means that a zone is defined by 6 real constants. Zones are convex polygons with vertical, horizontal, and 45-degree edges. At most, they have 6 edges. And the main theoretical result of Formats1 of our paper in Formats1 was that the match set for any time regular expression on any signal is a finite union of two-dimensional zones. There was an algorithm to compute the match set from phi and W. I will describe it briefly because it's important for the continuation. It will proceed by induction over phi, over the expression. If the expression is just one literal, the match set is a union of triangles like that. Each triangle corresponds to the positivity interval in P. For example, for any 2 points from 4 to 7, such that t is less than t prime, the point t prime is good. It corresponds to some subinterval of this period. It gives this triangle. If we have a match set of phi, it's easy to construct its time restriction. It suffices to intersect the match set with the diagonal stripe t prime minus t is in the interval. For example, here I draw the intersection of the previous set of triangles with a stripe 1 to 2, like that. Boolean operations are easy. Indeed, if a union of two unions of zones is a union of zones. If you want to do intersection, you should intersect each zone in the first union with each zone in the second one. And intersection of two zones is a zone. A complement is a bit more involved because naturally it gives an it requires to intersect many to intersect many unions of 6 zones. Anyway, it gives a finite union of zones at the end. What else? Concatenation. Concatenation in fact on match sets corresponds to composition of binary relations on zones. Such a composition also yields a zone and can be obtained using standard zones operation. Geometrically, it's such a strange operation. Take this triangle, this trapezia, and obtain this pentagon. Iteration could seem unfeasible because you need iterate a relation an unbounded number of times. But when there is the duration is restricted, we can show that union of n zones should not be iterated indefinitely. It suffices to do it n plus d over c times, where c is the smallest constraint in definition of R. This number of iteration is not very huge, especially because we can compute the power Rk, Rn, and the closure R plus by squaring, and it requires only logarithmic number of squaring. Let's show that our structural induction really works on our first example. We have a signal, we draw match sets for pi, the green one, for q bar. We intersect pi and q, it gives the blue triangles here. We concatenate with q bar, it gives these rectangles there. With q again, the green rectangle. We restrict the time, it gives the small triangle. And we concatenate again with p bar, which gives this square, which is the match set for this equation on these signals. This is the algorithm of Formats1. Now we want to analyze the complexity of the problem. More precisely, given a signal W written in binary with binary rational dates, and an expression with integer timing intervals written also in binary, we want to answer the question: does the whole signal match the expression, or maybe some other question? Is there a match set? Is the match set non-empty? Is there a suffix or a prefix matching phi, and so on and so forth? It turns out that all these variants of the question are always in the same complexity class, so we will concentrate on the bold-face question: does the whole signal W match phi? Given the algorithm presented before, why is this analysis not completely trivial? First of all, the algorithm presented was manipulating sets of zones. How many zones in a set? Does it explode or not? On the other hand, the duration in a signal and the duration in the expression can be big because they are written in binary. The number of events is moderate, but the duration can be exponential. It gives rise to big arithmetic problems. And on a very high level, the problem involves a combinatorial and arithmetical aspects mixed in a strange way. Okay, let's go ahead. The first question, the first observation is to look at the match set and to say something more that was said. So let us have a signal with n events, a duration d. And let phi be a regular expression. The match set is, of course, as I said, a union of zones. A zone, each zone includes 6 constants. Let us try to understand what are constants that can participate in the match set. By induction, we can prove that only T, which is this set, plus integers or just integers and all that belonging to 0D can play a role in the definition of such zones. So we have only dn constants that can participate in their definition. We will draw a picture with all the minimal such zones defined with these constants. In this picture, we will call these minimal zones regions. Each zone is a finite union of regions, and there are d square and square such regions, as shown here. Here we have a set of constants. We draw a vertical, horizontal, and diagonal grids, including these constants. And all the cells, all the small cells in this grid are regions. Each zone is a finite union of regions. It means that we can see every match set not only as a union of zones, but also as a union of regions with a pre-constructed set of n squared d square regions. Notice that differently from Allure and Dill's region graph, the form of this region set depends on the signal. It is determined by dates of events in the signal W. Now, finally, I can formulate our main results. The first theorem says that if the duration is polynomial, if it's given in binary, time and pattern matching, even using all negation, intersection, and so on and so forth, is easy and can be solved in polynomial time. The second result says that without polynomial bound on the duration, disjunction, concatenation, and time restriction suffice to get NP hardness. And the problem remains NP complete even if we use intersection. There is no star here. Finally, in the general case, as soon as we introduce the complement, with or without iteration and intersection, the problem is a p-space complete. Let me sketch the main proofs. The first case, when the duration has a polynomial bound, is based on revisiting our recursive algorithm that I already presented, or our old algorithm that we will lead using region sets instead of zone sets to represent each match set. So we will proceed recursively to computing match set of a timed regular expression. For a literal, we will just return a set of triangles. And all operations are what they should be. Union, intersection, complement, time restriction, concatenation. Every time we proceed with sets of regions. The only difficult thing, which is Kleene plus iteration, is done by squaring, by recursive squaring, using the bound I have described it before. Everything here is polynomial. Now we remove the bound on the duration, and we prove that the problem becomes NP hard, even without iteration. We will use a well-known subset sum problem, which is NP complete, given a set of naturals and the target natural M, that there exists a subset with sum equal M. I will write it like that. Can I choose 0 OA1 plus 0 OA2 plus 0 OAK, that the sum is M. Zeros, I don't like them, so I will augment everything by 1. It's another equivalent version of the subset sum. I will augment everything by 1. The left-hand side will be augmented by k. So this is another form of a subset sum. And now I write it as time pattern matching. I will take a signal which equals p during m plus k time units. I will try to match this expression, which is exactly the same as the previous formula. I can match if and only if there is a subset with sum equal m. So I have reduced an NP complete problem to my TPM. Thus, the TPM is NP hard. Now I will show that without iteration and complement, TPM is NP easy, is in the class NP. For that, I will write a non-deterministic procedure. This deterministic procedure, given and time at regular expression phi, and the signal W, of course, will guess and return a matching region, and it is capable to return any matching region. If there are no matching regions, it will fail, of course. So if the formula is just P, we will guess a region in the triangle corresponding to P. If it's a disjunction, we will guess a disjunct. We will guess a match corresponding to the disjunct, and we will return it. If it's a conjunction, we will guess a match for the first conjunct, guess a match for the second conjunct, test, check that this is the same match, and return it. For duration restriction, I guess a match for psi. I check that it is included in the required interval, and I will return. And if it's the case, I will return this guess. Otherwise, I will fail. Similarly, for concatenation, I will guess match for the first part, match for the second part, compose them, guess a region in the composition, and return the result. It's easy to see that representing my region with polynomially many bits, I will do all this in polynomial time. At the end, I must check that the whole interval 0D belongs to the guessed region. This is fine, but this does not work with a star, with the iteration, unfortunately. Now the last theorem is about p-space. We add complement to our regular expressions. We will use a reference problem due to Fearnley and Dzyurzynski called subset sum game. It's given n numbers A, B, C, and D, and the target number W. We want to check, the first player chooses A1 or B1, the second C1 or D1, and so on and so forth. And finally, the second player wins if the sum of all the chosen numbers is W. This conjunction disjunction can be written using complements like that. And P during time W, the signal, the constant signal, matches this expression with many embedded complements if and only if the reference problem admits a positive answer. So we have reduced a p-space hard problem to our TP time pattern matching. Finally, why our general negation and iteration time pattern matching is in p-space. Or for that, we write the recursive algorithm yet in another form. Now it will be a deterministic procedure which, given an expression, given a signal of course, and given a region, answers whether the region is included to the match set. It is in a way inspired by classical theorems on space complexity like Savage and so on. It's easy for a propositional constant, it's easy for disjunction, it's easy for complement and time restriction. It's more fun for concatenation. If we want to check whether R matches psi1 concatenated with psi2, we will, in a big for loop, enumerate all the couples R1, R2 of two regions. And if R1 is matches psi1, R2 matches psi2, and R is included in R1 concatenated with R2, then we say yes. It is a very long loop, but it takes a small memory fingerprint. As for Kleene, we also proceed by squaring, and we do this squaring enumerating all possible. We reduce inclusion to for phi iterated 2 to the kth power by two times smaller problems. These 2 times smaller problems for this which we will enumerate all potential regions, one for the first half, the other for the second half. And if R is included in R1, R2, R1 is in the iteration for a short prefix, and R2 in the iteration for a short suffix, then we know that R is in the iteration of the whole long of the long iteration of the whole long word. thus, it's easy to see that since regions can be written in polynomially many bits, since the recursion dips is polynomial, all this can be done with a with a polynomial size stack, and in general in P space. Okay, the theorems are more or less proved. But unfortunately, the most interesting, the most natural case is still in a gap. Pattern matching of expressions with disjunction, concatenation, and iterations, with or without intersection, is NP hard and P space easy. We still don't know what is the complexity. The only thing that we can prove is the in NP bound, NP completeness, when we fix the depth of the plus of the iteration. In techniques, this proposition is very similar to the theorem by Hazel and Zetsche about Pressburger arithmetic with star. Also, they also have NP completeness for fixed star depth. I conclude now by summarizing new things that we know today and future work. We have understood that our old recursive algorithms, which were efficient in practice, are indeed in the class P if we fix a bounded duration. We also have identified difficult cases. We learned that big numbers, big duration lead to NP completeness, and that negation leads to P-space completeness. We have discovered that the match set are not so wild as they could be. They are union of a set of regions. We also have found some links with a regular expression on real numbers. In fact, our complexity results can be directly ported to subsets of real numbers, as described implicitly by this regular expression have been described implicitly by Chauffreux and Goldwurm and explicitly by Catalin around 2000. We have also understood that our problems are related to more recent works on existential Pressburger arithmetic augmented with star. And we have some future work, close the gap, find the complexity which is as we know between NP hard and P space easy. Extend this to other formalism for timed patterns, such as various interval logics, and try to understand how this theoretical analysis can serve in our tools and improve practical timed pattern matching. Thank you.
Thank you very much, Eugene, for this very nice presentation, pre-recorded, and it's also a very interesting presentation. So I think we already have one question from Martin in the Q&A session. If you can have a look.
Yes, so Martin asks, can you hear me? Yeah.
Yes.
Yeah. Okay, Martin asks, would these results carry over to a setting where a TRE is matched against another bounded in total duration TRE instead of a concrete signal? I believe that in general, pattern matching, even for discrete words, is much easier than comparing two expressions, than than answering any language problems such as emptiness or something. For example, when you allow in discrete case, when you allow intersection, complement, and so on, even emptiness, it becomes awful non-elementary.
Yes, right.
So in fact, I believe that as soon as we have two expressions, it boils down to a sort of inclusion of timed languages. Even on restricted automata, it should be difficult.
Right.
So my gut feeling is that the answer is that it's that the complexity should be higher than p-space, or p-space maybe for some very restricted.
Yeah, I agree. Thank you so much for the answer. I agree that as soon as you are having negation, of course, this should be true. Then in some sense, it must be non-elementary at least, right? But we could also, of course, restrict negation in one of the two, maybe in the expression describing the set of signals. So do you have any idea of what happens then if we don't have any negation in there, just positive statements about a possible set of signals?
You know, what would be difficult is thinking about the star. When you have one given signal, you can bound the number of iterations. When you have two expressions, I'm not so sure. So
Right.
even to prove decidability can be a challenge. But it's a very interesting question. Thank you.
Okay, thank you.
So we have another question from Masaki.
Masaki, what does he ask? Piecewise constant or piecewise linear real valued signals. Maybe Dejan could answer. He is a panelist. I believe he can activate his mic. No, is he here?
Yes, I'm here. Let me just read the question.
Yeah, my question is like if such a complexity discussion on Boolean signals can be some partially extended for piecewise constant or piecewise linear real value signals.
I think if you have a concrete signal, it should not affect these complexity results, because you would first Booleanize something that you can do in polynomial time, in linear time, and then you would apply what Jean presented on the Booleanized signals.
But actually, like what I was imagining was more like to answer the robustness instead of the Boolean satisfaction. But how do you think about
so you would like to find instead of the matches, you would like to find this quantitative.
Indeed.
My feeling after performing this work that it requires some thinking, that it's a good master internship subject. So it does not look difficult. It requires some work. You should think also about I don't know, rationals that appear there and so on and so forth. But I believe that one can extract something like that. But in fact, we never thought about that.
No, we didn't think, but there is this paper of Oded and Thomas, and I think also Don, where they compute the robustness of what they call signal regular expressions with respect to a given trace. But as far as I remember, they do not consider the complexity issues. I don't know if you were you also the co-author on that paper,
Not me.
Okay.
As far as I remember.
But I would also like to come back to Martin's question because I was thinking it's not even very clear if you have a set of signals. What does it mean to have a match over a set of signals? Would we consider it kind of existentially as a union of all the potential matches of all the signals? And
Yes, this was my interpretation. So you're describing a set of signals. You will ask what intervals would possibly match to one of the instances.
No, the classical questions, inclusion or something else, are classical questions in complexity theory. Why not? It's interesting as at least as a mathematical problem.
Thank you. Thanks very much for the answers. And let me thank you again, Eugene, for the very nice presentation. And thank you all for attending this session. So I think we can come to close it. Thank you. Bye-bye.
Thank you.